All right, hello everyone. So today we're going to talk a little bit about binary search trees, and more specifically, we're going to talk about how to traverse them. We're going to talk about the in order, the pre-order, and post-order traversals, and then lastly, we're going to create and implement a breadth first traversal. Um, so, a little quick thing before you get into this, you should at least know a little bit about trees. You don't have to know too much, but more importantly, you should be fairly comfortable with recursion. You don't need to be a genius at it or anything, but you just need to know sort of basic recursion and that when we call a method from inside itself, it's going to stop there. It's going to add a method call on top of the stack, and then it's going to keep doing that until it runs to its end, and then it's going to get popped. Then, of course, we need a base case. So basically what I'm trying to say is just if you're not comfortable with recursion, maybe just do a quick little update and then come back to this one, come back to this video, and we'll be good to go. Right. So trees. So generally, first we're going to talk about trees, a little bit about trees, just to make sure we're all in the same language or on the same level. And then we're going to talk about what a binary tree is, and then we're going to talk about a binary search tree, and then we're going to go ahead and implement it. Right. So in general, a tree has three rules that it tries to abide by. Each tree has a root node. If you're unfamiliar with what a node is or what it's supposed to be, don't worry. We'll be quite literally programming a node, so you'll be able to get to see it like that. So each tree has a root node, and that root node has 0 or more children, and then each child node has 0 or more children. Now, again, that's a pretty abstract way to describe things, but in general, a tree usually looks like this. Now, what we have here is a binary search tree. That means there's a specific set of rules put on this tree to make a binary search tree. So not all trees look like this exactly, but they usually all have a non-linear hierarchical structure like this, right? They usually has start somewhere and then it has branches off like this. Right. So when we talk about binary trees, the thing that makes the binary tree unique is that each node has, at max, up to 2 children, which is not a normal requirement for all trees, right? You'll probably go through, you'll see trees. I believe there's a tertiary tree. I believe that's what it's called, where it has 3 children, and so on. There's lots of different types of trees. They don't have to have or have a restriction where they are forced to have 2 child nodes. And then we move on. When we talk about the binary search tree, a binary search tree has the same child restriction. So the child node restrictions as a binary tree. But what makes a binary search tree unique is that the binary search tree nodes, they must abide by a very specific ordering specification. And that being that each left child node must be less than or equal to n, and then the n must be less than the all right child descendants for each node n. Now, I might not have done the best way describing that, so let's go ahead and look at this image here. So what I say is that when all left descendants must be less than or equal to n. When we talk about n, we're just saying whatever current node we're on. So all left descendants must be less than or equal to n. So that's true. And then n must be less than all right descendants for each node n. So what that really means is that whenever you're at a node, when you go to the left, that means the nodes underneath it are going to be less than or equal to it. And when you go to the right, it's going to be greater than it. So nothing too complicated, but what this specific ordering allows us to do is just allows us for more a lot more efficient searching. And without that ordering, you really start to lose all the efficiency that you have with a tree when you're looking for a specific node. Right. With that being said, we'll probably go ahead and get to this first bit here. We want to go ahead and create this node. Now, this node is going to be, we're going to have it a private class. We're going to call it node. It's just going to be a pretty basic POJO, a plain old Java object. It's going to contain an element, private, and then a node, left child, and we're going to say private node right child. I just realized I spelled left wrong here. Right, so as you can see, each node is going to have an element and then a left child reference and a right child reference. As you can see, that's exactly what this node has here, right? We have an element here, and then we have a left node, or a left child reference and a right child reference. Now, when I say this is a plain old Pojo object, all we really need to do is memorize this, and now we can just create a constructor. So we'll say public node, and then it's going to be int element node left child and node node right child, and then we just sign those. This dot element is equal to element, and we do this dot left child is equal to left child, and of course this dot right child is equal to right child. Awesome, awesome. And then we just go ahead and we define the setters. So we'll say setters, we'll say public void set element, and we're just going to give this an integer of element. We'll just do this dot element is equal to element. Just scroll down here a bit, and then we'll say public void set right child, set that equal to right child, and then again public. Let me just scroll down here, set left child. Awesome. So now we get these setters, getters. So we'll say public int, we'll say get element, we'll say public node get left child, and then public node get right child. Awesome. So now we have these getters, we have these setters. So this is our node completed. So I'm just going to go ahead at the bottom here. I'm just going to add this line so it's a little less confusing for myself. I'll just say end of node class, end of node class. And then next thing, so we can go ahead. We've finished this node, so we can just go ahead and delete it. Now we can move on to creating the insert method. Excuse me. So now we go ahead. The first thing we need to do is excuse me. So now we need to go ahead. We need to work on this insert method. But the first thing that we have yet to add is that every tree usually has a reference to its root. Remember we talked about the root before. The root is really just the first node added. So you can see here, this 8, this would be the root. So we need a reference to that, of course. So we can say node, we should set that to private node root, and we're going to set that equal to, initially we're going to set that equal to null, because for us, when the root is equal to null, that means the tree is empty. And then lastly, you don't have to put this, but we're just going to do, we're going to say int size is equal to 0. So just so we know how many nodes are inside the tree. Now we can go ahead and we can go ahead and I guess we'll just start and create the insert method. Now this insert method, I'm gonna break it down into 2 methods. We're gonna send a public facing method for API, and then an internal one which does a little bit more of the work. So we'll just call this insert. We're going to take an int element. Oh, right, because I've already had this method set up here with some values. Yeah, I forgot to specify the return value. So void. So now we can go ahead, and first thing we're going to check, first thing we're going to do is we need to create a new node, right? So we'll just call this node, and we'll say new node, and we're going to set that equal to a new node. And then we pass the element, and then since we don't know, it doesn't have any children, we don't know where it's going, we can go ahead and we can say null and comma null. Awesome. Now we just do a check we do a null check for the root. So if this dot root is equal to null, essentially here we're going to have two cases. We're going to have the case if the root is null and if the root is not null. So if the root is null, all we do is we say this dot root. We're going to set that equal to the new node. And then else, we're going to call another method here. This is the other method I was talking about. We're going to say insert node, and we're going to say this dot root. Notice because we just haven't created it yet, and we're going to call the new node. Awesome. And then no matter what, since we already put size, we're just going to increase size. So now we can create the private method. We can go ahead. We can say private. Insert node, I should say, define its return type. I've been using too much Kotlin. Public void, we need to say insert node. We need to go ahead and, of course, it needs a node, and we'll say node of new node. Right, so now there's first thing we need to check here, right? So when we're given a value, the first thing we need to determine is where it goes. So let's just say we have this here. We already have something laid out, and then we want to add 2 to it. So where would 2 go? Well, we'd first have to check, okay, we'd have to check the element. Okay, it's less than 8. Okay, so that means we're heading down the left side. Okay, it's less than 3, so that means, again, we're heading down the left side. Okay, it's greater than 1, so it means we're heading to the right side, and since there is no value there, we can assign it to that value. So essentially, how do we translate that into code? Well, we do that with some good old-fashioned conditionals. So the first thing we need to do is we need to determine which side we're going to go off of. So we need to say node dot get element. So if node dot get element is greater than new node, new node dot get element. If that is the case, that means we're heading down that left side, right? So then we need to check if that node dot get left child is equal to null. If that is equal to null, that means that there's a place for it to go, so we just assign it that place. So we say node dot set left child, and we set that equal to our new node. Now, this might seem a little odd here, but this is actually our base case. Now, I say base case because now we're going to do a little bit of recursion. So if that is not the case, we're going to do some recursion. We're going to say insert node, and we're saying node dot get left child, and we're going to go, we're just going to call our new node. So what this essentially has us doing, right? Let me just shrink this a bit for us. Move this down a tiny bit. Move this up. Yeah. Okay, so what this has us doing is we're going to, let me just go move this a bit. There we go. So what this has us doing is we're saying, so first thing we're going to check, just imagine, right, we're going to insert 2. So we're going to go ahead and we're going to say if that node dot get element, our node again is going to be the root, right? We pass it this root here. So if this node dot get element is greater than the new node get element, and of course our new node is 2, we're going to start off with 2. That means we're headed down this left side. So then, okay, so then we're going to check if this node dot get left child is equal to null. So we're going to say this node, and we're going to get its left child, and we're going to say, is that equal to null? That is not the case. So else we're going to call this insert node with node dot left child. So we're going to call this, so we're going to have a new method call, but this node call is going to be 3, and this is going to be our new node. So again, we're going to make a recursive call. So that means we're essentially going to stop what we're doing, and we're going to call this method again. So okay, now this node is 3. this node is what we have here, and this new node is the same old new node that we inserted. So again, we're going to say if new node.getElement is greater than new node.getElement, which again is going to be true because we're inserting 2. So we're going to skip this out, and we're going to make another insert node call, which is again is going to be a recursive call, and then we're going to call it with that node.leftChild, which is going to be this 1. So again, we're going to have a call with 1. But then we're left with, okay, how do we get to the right side, right? Well, actually, when we get to the right side, it's quite literally just the exact same thing here, just in the else block and with the right. So we just go else. So we just grab this, we just put this here, and then we just change the right child. We change all the lefts to rights. Right. Right child. Right. Awesome. Yeah. So when we go ahead and we actually run this, I've actually added this, so it's going to create the exact same mockup as what we have here. So you go ahead and run it now. It'll be fine. It should run, yeah, as you can see, we have no errors or anything, which is really nice. So now that we have our insert method, we can go and do this, create this, go ahead and create the pre, the in, and the post traversal methods. So again, with these methods, I'm going to break them down into 2 more methods, a public facing one and then an internal one. So we're going to say public, again, void. I'm going to do in traverse first. In traverse. Sure. Actually, it should be in order. See, in order. Now, this in order traversal, it's actually going to deliver everything in ascending order, meaning it's going to get the smallest to the largest. So again, with this, we're going to be doing some recursion, but just hold on. We're going to say if this dot root is not equal to null, is not equal to null. So essentially, since we have this running void or returning void, we don't have to do anything. We're not having it return a specific value. We're just actually going to print out everything. So we say if this dot root does not equal null, we can go ahead and now we could run our other method that we've been talking about. So we could say in order traverse node, we're going to say this dot root. We're going to start it off with the root. So we'll go private. We'll make that method now. Private void in order traverse node, and we'll say node. Right, and then as long as if node does not equal null. So again, this is our base case. As I said, we're going to be doing some recursion. Then all we do for the in order traversal, it's super simple. We just do this, in order traverse node, and then we just say node dot get left child. And then again, we system.out.print .ln, and we say node dot get element. Now what this is going to do, this is going to travel all the way down to the smallest element first. So this is just us basically traversing all the way down this left side, traversing all the way down to this left side. Then once we get to this left side, the base case is going to be called, and then we'll move to this. Then we'll print out that element, and then we'll go ahead and we'll get the right element. So instead of this left, we'll go right child. Right, so when we go ahead and run this, so we'll just go ahead, we'll say tree dot in order traversal. So when we go ahead and run this, we should get 1, 3. Essentially, it'll be in ascending order, right? It'll be from smallest to biggest. So let's go ahead and we'll just run this. Yep, so as you can see, we got 1, 3, 4, 6, 7, 8, 10, 13, 14. Awesome, exactly what we wanted. Now, I'm not going to code out the pre-order or the post-order traversal because the only thing that differs from them is when they actually visit the node. And what I mean is that pre-order traversal is just that. That's exactly what pre-order traversal is. And then post-order traversal is that. So it's quite literally just one line change. That's not really too hard or too interesting. Where things start to get interesting is when we move on to this breadth first traversal. So now that we've created this pre, this in, and this post, let's go ahead and create that breadth first traversal. Now, this traversal, we're not actually, what that means by breadth first. So what we've been doing with this in order, pre-order, and post-order, we've been doing depth first traversal. So essentially we're going down, as far as we can down to the bottom. But with this breadth first traversal, that's not what we're doing. We're going to be traversing by depth. So that means depth is calculated by how many ancestors a node had. So this is a depth. 3 and 10 has the same depth. 1, 6, and 14 has the same depth. And 4, 7, and 13 have the same depth. So we are not going to be recursion. The way we're going to do this is we're going to use a queue. Now a queue is special because it has the first in, first out principle, meaning that the first thing you put inside a queue is the first thing you get out. It's the opposite of the first in of the stack, which is first in, last out. So inside this method, I'm going to be using a utility method, so called children, which essentially is how we're going to get the children of each node that's going to be added in a queue. You'll see when we do this, but essentially what we're going to do is we're going to have a node, add it to the queue, and then we're going to remove it from the queue, and then we're going to add its children to the queue. Then we'll remove it, then we'll add its children to the queue, then we'll remove it and add its children to the queue, so on and so on. So with that being said, let's first make that utility method. So we'll solve private. It's going to return a list of node. It's actually very important here. We'll call it children. It's going to take a node of node. So it's going to return a list. So let's first return that list, or we'll create that list. We'll call it list, and we'll set it equal to new array list. We'll set that equal to 2, which is, of course, the initial capacity. We don't need it actually bigger than this. So we can go ahead and we just need to check if each node has a child or not. So if node.get left child does not equal null, we do list dot add node dot get left child. Awesome. And then we just do the exact same thing, but with the right child. So go ahead, get right child. Then again, get right child. And then lastly, we just return that list. Right, now we can go ahead and head into this breadth first search. We'll say public, actually we want this to return a list. List of node, breadth first, traversal. Right, so the first thing we want to return a list of the properly ordered breadth first traversal. So we're going to go ahead and we're just going to create that list. So it's going to be a node, let's call it breadth list, and it's going to be equal to a new array list. We're not going to give it initial capacity because we don't know how large it's going to be. Right, then we need to check if the root is equal to null. So if this dot root does not equal null. So if does not equal null, that means we can go and start doing our party. But no matter what, we want to return this breadth list. It might be empty, it might not be. So now that we're inside this, we can create our queue. So QUE, we're going to parameterize it with node. We're going to say it's going to contain nodes. We just call it QUE, and we're going to set it equal to new linked list. Now, that seems really weird, right? But Q is really just an interface, right? So we're just using polymorphism here. We're able to set the Q essentially on top, the Q interface on top of the linked list. So we're accessing the linked list as if it was a queue through its Q methods. So not too bad. Then what we have to do is we're going to add the root to the queue. So we're going to say queue actually, QUE dot add this dot root. Right. Now that we've done that, now is where we actually start doing the work. We're going to create a while loop, and we're going to say while QUE dot is empty. We're actually going to negate that. So we're going to say while this queue is not empty, what we want to go ahead and do, we're going to want to remove the root from the queue. We then want to find its children, and then we want to add that children to the queue. So first thing we're going to do is we're going to say node is equal to QUE dot remove. We're then going to, actually I forgot this, we're going to add the breadth list dot add into this node, right? And now what we're going to do is that now we've removed it and we've added it to our breadth list. We want to find its children. So we're going to do this for each loop. So we'll say for node n inside the children method, right? Remember this utility method that we called? It takes a node, so we're going to say node. And we're going to add QUE dot add this n. And that's it. That's our breadth first traverse. So what we're doing here, right? What we're doing is we're adding the root to this queue. We're then entering this while loop. We're then removing the queue, the node from the queue. But remember, the while loop conditional doesn't get computed to the end, so it's still going to run. We then add it to our breadth list. This is how we are getting the proper ordering. So we're adding to the breadth list. We then want to get each child. Now, each child is going to be on its own depth, right? So what this means here is so we pretend, or this is actually the node on the initial call, correct? So what we do is then we get its children and we add those to the queue. So first thing we do is we add this root, we then remove it, and then we get its children, both its children. And then, since the queue is first in, first out, we then are going to repeat the process for each of its children. First we'll do it for 3, and then we'll do it for 10. And then so on, then we'll do it for 1, then 6, then 14, and then 4, then 7, then 13. And then the way that it stops is eventually once it gets to the bottom where everything is null, there's going to be nothing left added to the queue. And since we're removing things from the queue, it's eventually just not going to be added anymore and the while loop will break. Right, so I'm actually so breadth first traversal. I'm actually just realizing now that we're not going to be able to traverse this, or we're not going to be able to see this. So I'll actually do a system.out.println. That's actually not what I wanted. We'll do a for node n inside the breadth list. We're going to, oopsie. I'm just doing this right now, so just so we can see something inside the console. So we'll say system.out.println. We'll say n.getElement. So finally here, this is just us. So I'll be able to show you that everything is inside the proper ordering. Right, so when we go ahead and run this, we should see 8, 3, 10, 1, 6, 14, 4, 7, 13. So let's go ahead and run that. Let's get back to here. Yep, 8, 3, 10, 8, 3, 10, 1, 6, 14, 1, 6, 14, 4, 7, 13. 4, 7, 13. Awesome. That's exactly what we wanted. Now, that is it technically, but I guess you'd probably, like, if you wanted to turn this into a breadth first search, probably the way you could do this, I'm just trying to think here. I actually just got thinking, I was like, this would probably be a good search. So anyways, we could probably turn this into a Boolean. Make this return a Boolean. We just have you return false. Get rid of all the breadth list stuff that we do because we don't need it anymore. Breadth list, breadth list, breadth list, breadth list. Delete, delete, delete. Now, we're still gonna do everything. We're still gonna add it to the queue. But where would we check this? Okay, so we'd want to check. So we'd say if node dot get element is equal to, and then we need a target. So we'll set a target here. So we'll say int target, and then it's equal to our target. Sorry, I'm not explaining this very well. I just need to think there. All right, so we'll get into it now. So, and we'll just say return true here. Right, so what we did is we went ahead and since we want to do a breadth first, we could actually just go ahead and call this traverse or breadth first search. Right, so since we're doing a breadth first search, it's going to be exact same as the traversal. The only thing is that we're just getting rid of all the breadth list stuff that we're doing. We want to search for an individual value, right? So now we do so inside this while loop. And then so we remove the node from the queue, and then we check to make sure if that is the node that we wanted. Now, the reason that I'm doing it here and not inside this for loop is because I believe that if we do it inside this for loop, we're not going to be able to, it'll return false for the very first value because this is just the children. Yeah, so let's go ahead and run this first. Search system.out.println. We'll go ahead and run it like that. Oh, we need a target, right? So the target will be 8. So we go ahead and run that. So this will return true. It should return true. Yep, we get true right there, which is awesome. We'll then just do for search like 88 just to make sure. Awesome, so it returns false. Now, the reason I didn't do it inside this for loop, so if nodes, let me just do this. Because we're not, this node is actually going to be, the node returned is actually going to be the first child. So it's not going to be 8. Instead, this first node returned is going to be 3 and 10. So the very fact that we're inside this for loop means that we're not going to have access to this 8. So now when I go ahead and run it, we're looking for the target 8. Previously we got true, but now we go ahead and run it and we're probably going to get false. Oh no, we got true. Awesome. Okay. So I guess it doesn't matter then. That's pretty cool. Target 8, 8, 8. Awesome, 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 awesome. If no duck elements, yeah, cool. Yeah, so I guess you can put it either or. All right, so I believe that's everything. I'll leave a link down in the description below to the GitHub where I posted this all. Geez, this is like a solid 100 lines of code. But the next video, I want to do some leak code. I believe there's trees. problems. Maybe if I do LeetCode trees. LeetCode trees, yeah. So the next video, what I've planned to do is I want to do these trees. There seems to be a lot of these tree problems. Yeah, actually, there's 202. And a lot of the easy ones, a lot of them have seemed to be dealing with traversal. So max depth, you saw it there. Average levels of a binary tree, some root. Root equals sum of children, some range of binary search tree, find all the lonely nodes. So yeah, so this is really just to get us started. And the next I'm going to be doing a lot of, I'd like to get all of them done, but definitely I'll do a couple easies and then we'll try some mediums. And then maybe if we're feeling spicies, we'll try the hard. Right, so that being said, thank you for watching and I'll see you in the next one.